We are in Chapter 6, Additional Topics in Integration. Section 6.1 is Integration by Parts and Integral Tables. The technique of integration by parts allows us to reduce a complicated integral to a simpler integral. And so we're going to go ahead and give our box a star here and put our formula in. Integration by parts says if u and v are differentiable functions, then the integral of u dv is equal to u times v minus the integral of v du. And so this is definitely a formula that we need. This allows us to integrate by separating things into parts. If you notice, we have u times dv, and so what we're going to do is separate this, find out what u is, find out what dv is, and then we're going to have to take the derivative of u to arrive at du, which we need in our formula, and then integrate dv with respect to v to arrive at v. So we have some conditions for integration by parts. The integral can be written as the product of two factors, and those are called u and v. And it is possible to integrate dv to get v and differentiate u to get du. The integral of v du can also be found, or you might have to do integration by parts a second time in order to find your final answer. So the first example that we have says the integral of x times e to the negative 2x dx. And if you were to try to let u equal the inside function and let u equal negative 2x and go through that route, you would also be stuck. So you would actually be able to use substitution, but it wouldn't allow you to actually integrate this and find an answer. So we need another way to deal with this problem. So we're going to go ahead and write let u equal and dv equal. So we need to figure out what to let u equal and what to let dv equal to. And we're going to separate this into two pieces. So I'm going to go ahead and pick u to equal x. And the reason why is because when I take a derivative of this with respect to x, I just end up with du is equal to dx. And that means that this leftover part over here, which is e to the negative 2x dx, needs to be integrated. So I'm going to integrate this on the left side with respect to v, and I arrive at v, and integrating with respect to x on the right side, I end up with e to the negative 2x divided by negative 2. I am not going to put c with my answer here when I integrate. The reason why is because we're not done with this problem, and this is only part of it, and I will put my plus c at the end when I am done and find my final answer. So at this time we're trying to integrate x e to the negative 2x dx, and our formula up above, if you take a look at that, is the integral of u dv is equal to u times v, which are these two multiplied together. And so I'm going to go ahead and write this as x times, I'm going to write this e negative 2x divided by negative 2. Put them in parentheses so you can see that we're multiplying. And then it's minus the integral of v times du. So v is e to the negative 2x divided by negative 2. And then if you notice du, which we found, is the same as dx. So if you notice, my integral that I have right now, and actually that whole expression that we have, is in terms of x's and not in terms of u's and v's. So from here, I'm going to go ahead and rewrite this. This is negative 1/2 x e to the negative 2x. I have a negative and a negative on the next term, so I'm going to go ahead and put plus, and I'm going to pull that 1/2 out in front. So I have 1/2 times the integral of e to the negative 2x dx. And then I can integrate this, and so that first term stays exactly the same, so I'm just going to bring that down. Plus, and I have 1/2 times, and then integrating this, I end up with e to the negative 2x divided by negative 2. I am now going to put my plus c. From here, I can clean this up a little bit, and we arrive at negative 1/2 x e to the negative 2x, and then minus 1/4 e to the negative 2x plus c. So you can definitely leave your answer this way. Otherwise, you can factor out the smallest factor that we have and the common factor that we have. And so the smallest number that we have here would be negative 1/4. And then we also have e to the negative 2x. So left over, we have 2 times x plus 1, and then a plus c. So either of these answers are fine. I'm going to go ahead and box that first one. You can also check the second way that I've written the answer by distributing that back in to see that you arrive at the one that we have boxed. The next example that we have says to find the integral of ln of x dx, and we don't know how to do that, so I don't have anything that will work in order to set u equal to in order to try my u substitution. You always want to try u substitution first, and then if u substitution does not work, then you would like to go ahead and try integration by parts. So since we can't use u substitution on this one, we're going to go ahead and set let u equal and dv equal. So I don't have much in this integral, and I clearly cannot integrate ln of x, so that means that ln of x is what I'm going to have to set u equal to. Left over, I have dx, and that is what I'm going to have for dv. So the whole entire integrand, what you are integrating, should be split up into u and dv. From here, taking a derivative of the left side, I end up with du, and of the right side, I end up with 1 over x dx. Integrating the second equation that I have, I end up with v is equal to x. From here, we have the integral of ln of x dx is equal to u times v from our formula. So I'm going to have ln of x times x, putting those in parentheses, minus the integral of v du, which is going to be x times 1 over x dx. From here, I can simplify this. I'm going to go ahead and put that x out in front here. It doesn't really matter, but it does clean it up a little bit. And then multiplying these, they cancel. So I end up with the integral of just dx, or the integral of 1. And so I end up with x, ln of x, minus, and since we're integrating this with respect to x, we get minus x, and then plus c. You could definitely factor out an x if you wanted to. I'm just going to go ahead and box this and say that we are good, but that is an equivalent answer that you can rewrite this problem as. On the next page, we have another example. This example says the integral of 3x squared plus 4x times e to the 2x dx. So I'm going to go ahead and let u equal, and I'm going to choose to let u equal 3x squared plus 4. And the reason why I'm letting it equal 3x squared plus 4 and not e to the 2x is because when I take a derivative, I actually get a smaller expression. It goes from having a power of 2 to just a power of 1. Whereas if I were to take the derivative of e to the 2x, it just constantly repeats itself. And so yes, we might end up with a number out in front, but it still has e to the 2x. So I'm going to go ahead and write the e to the 2x over here in the dx. So I separated this with u equal 3x squared plus 4, and then e to the 2x dx, the other part of it, is my dv, which again we need to integrate. And I get v is equal to e to the 2x divided by 2. So from here, I'm going to rewrite my integral that we have, and I'll rewrite that first as the integral of 3x squared plus 4 e to the 2x dx is equal to, and this works out to being u times v, so we have 3x squared plus 4 times v, which is e to the 2x all over 2, minus the integral of v du, which is e to the 2x all over 2, times 6x dx. So from here I can clean this up a little bit. I'm going to put this as a 1/2 out in front, and then 3x squared plus 4 e to the 2x. And again, you can put the e to the 2x out in front also. 1/2 times 6 ends up with 3, and I'm going to move that out in front of my integral. And I have x times e to the 2x dx, which I'm still not able to integrate. So I am going to go ahead and switch colors now. And I'm going to say this part here we have to still integrate. And use substitution will not work on this one either. It looks very similar to the problem that we just did on the previous page. So I'm going to go ahead and try integration by parts again. So I'm going to let u equal x, and then dv is going to equal e to 2x dx. So taking a derivative of the left and the right side of the equation on the first equation that we have would be du is equal to dx. And then integrating the second equation that we have, we end up with v is equal to e to the 2x divided by 2. So from this little part right here, and we'll deal with the rest of it in just a minute, I'm going to end up with u times v, so x times e to the 2x divided by 2, minus the integral, and so we did u times v first, and then minus the integral of v du, so we have e to the 2x all over 2 dx. And then from here, simplifying this, I end up with x times 1/2 e to the 2x minus 1/2 out in front times, and then I'm going to integrate this, end up with e to 2x divided by 2. And I'm going to go ahead and put my plus c because at this time I am done with my integrals and I don't have to stress about that constant anymore. So I'll put that in. So I have this simplified as 1/2 x e to the 2x minus 1/4 e to the 2x plus c. So I am going to now have to put all of this together. I'm going to switch my color back to black, and I end up with 3 over 2x squared e to the 2x when I distribute in the 1/2 and the e to the 2x. And then 1/2 times 4 is going to be plus 2 e to the 2x. And then I have a minus 3, and that 3 is getting multiplied here to every single thing. I'm not going to multiply it into my constant just because a constant is a constant and it's just a value that we have. So we end up with negative 3 over 2x e to the 2x, and then negative 3 times negative 1/4 is going to become positive 3 over 4 e to the 2x, and then I have my plus c. From here, we can combine some like terms. We have 3 over 2x squared e to the 2x, and then minus 3 over 2x e to the 2x. And then I have a 2e to the 2x plus 3/4 e to the 2x. So we can combine these together, and to do that I need to get a common denominator. And so we end up with 8 over 4 plus 3 over 4, or 11 over 4 e to the 2x plus c. And from here I'm going to go ahead and box this, but you can definitely factor out the greatest common factor of e to the 2x, or you can factor out 1/4 e to the 2x also and write an equivalent answer. The next example that we have is now a definite integral, and this one says to find the integral from 1 to e of x squared ln of x dx. And this is going to work identically to what we've been doing with indefinite integrals, except for now we have to evaluate it and arrive at a numerical answer. So we're going to let u equal, and again I have to set u equal to ln of x, and the reason why is because I cannot integrate ln of x. So that means that my dv is going to be equal to x squared dx. So when I do this, I have du, and taking the derivative of ln of x, I end up with 1 over x dx. And then integrating both sides here, we have v is equal to x cubed over 3. So my integral from 1 to e of x squared ln of x dx is going to be equal to u times v. So we have ln of x times x cubed over 3 minus the integral of x cubed over 3 times 1 over x dx. And from here, simplifying this, I'm going to rewrite the first expression as 1/3 x cubed ln of x minus, I am going to simplify my x's. That's now going to become x squared. And I'm also going to factor out that 1/3. I have 1/3 times the integral of x squared dx. The other thing that I'm going to add in here that I didn't on the previous step is that this is a definite integral. So my integral is going to be going from 1 to e. So I will add those on. And also that first term that we have doesn't need to be integrated. It just needs to be evaluated from 1 to e. So I'll go ahead and throw that in. I am going to wait until the very end when I have my final integral, and I'm going to then evaluate it. And so from here, we have 1/3 x cubed ln of x minus 1/3, and integrating x to the second, we arrive at x to the third over 3. Again, I do not need to put a plus c because this is a definite integral, but I am going to say we're going to evaluate that whole thing from x equals 1 to e. I also want you guys to note that we didn't have to change the limits of integration because we did not change variables. I know we used a u and a dv, but that was to split it up and rewrite it, but it was still in terms of x's. So from here, I'm going to simplify this first and then we'll evaluate it. But we have 1/3 x cubed ln of x minus 1/9 x cubed. And again, evaluating this whole entire thing from x equals 1 to e. The upper limit of integration is what we're going to substitute in first. So we end up with e to the third times 1/3 ln of e minus 1/9 e to the third minus, and then evaluating this at 1, we have 1/3 times 1 cubed ln of 1, which is just 0, minus 1/9 times 1 to the third. So again, this is just 0. Ln of e is just 1. So we have 1/3 e to the third minus 1/9 e to the third minus negative 1/9. From here, this is going to simplify, and getting a common denominator here, you're going to have 3/9 e to the third minus 1/9 e to the third, or 2/9 e to the third plus 1/9. I'm going to go ahead and box this. You can also factor out a 1/9 if you would like and arrive at an equivalent answer. And also note that this is just a numerical expression here. You can plug this in on your calculator and actually get a decimal approximation and round it. The example that we have on the next page, we are going to go ahead and circle, and we will work on that one together in class. Right below that example, it says the rate of change of revenue in dollars per calculator from the sales of X calculator is, and we have a marginal revenue function. I want you to notice that it is the rate of change of revenue, so it is written as a derivative. Find the total revenue from the sales of the first 10 calculators, and then it says to round 2 decimal places since we are dealing with money. So I need to go ahead and set this up, and so I'm going to have an integral in order to get back from my marginal revenue or my rate of change of revenue to my total revenue function, and that is going to be 8x plus 4 times ln of x plus 1, and I am going to be integrating with respect to x, so dx, and my integral, since it's for the first 10 calculators, that's going to go from 0 to 10. And to integrate this, I can try use substitution, but it would be stuck. Since one is a logarithm and one is a polynomial, most likely is going to be integrating by parts. So I'm going to go ahead and let u equal part of it and dv equal part of this integrand. And so from here, letting u equal, it has to be the logarithm since we cannot integrate this. So I'm going to say let u equal ln of x plus 1. And then dv would be the leftover part that we have, which is 8x plus 4. And then we also have a dx. So taking the derivative of that first equation, we end up with 1 over x plus 1 times the derivative of x plus 1, which is just 1, times dx. And then integrating the second equation that we have, we arrive at v equals, and integrating this, we're going to have 8 times x squared over 2 plus 4x And I'm going to go ahead and simplify this and just write it as 4x squared plus 4x. So from here, I'm going to set up my integral, which is going to be u times v. Again, I'm going to use that one that we simplified down below. And u is ln of x plus 1 times v, which is 4x squared plus 4x, minus the integral of v times du. So v is 4x squared plus 4x, and then du is equal to 1 over x plus 1 dx. From here, I can simplify. If you look at this first part of my integrand, I can factor out a 4 and an x, and I am left over with x plus 1. My x plus 1s would reduce. So from here, I'm going to end up with the natural log of x plus 1 times 4x squared plus 4x minus, and left over I have the integral of 4x dx. And again, since I am dealing with a definite integral, I will go ahead and put on 0 to 10. And evaluating that first expression from 0 to 10. And again, I'm going to choose to evaluate this at the final, once I'm done integrating the whole entire expression. So again, I'm going to go ahead and move the 4x squared plus 4x out in front of the natural log, just so I don't get confused when I'm evaluating this. And I'm going to integrate 4x. So I have 4 times x squared divided by 2. And again, evaluating this whole entire expression from x equals 0 to 10. I'm going to simplify this a little bit. And again, I end up with 4x squared plus 4x times ln of x plus 1 minus 2x squared. And again, evaluating this whole entire thing from x equals 0 to 10. So substituting in 10, I'm going to end up with 4 times 10 squared plus 4 times 10 times ln of, and then 10 plus 1 is going to be 11, minus 2 times 10 squared. So that's evaluating my upper limit of integration. And then if I were to substitute in 0, the first expression part that we have, that first term would become 0, minus, and then 2 times 0 squared would also just become 0. From here, I would use my calculator to evaluate this, and when I do, it does say it around 2 decimal places, and so I arrive at 855.07. And again, since we are talking about total revenue for the first 10 calculators, we have $855.07. So it says find the total revenue for the sale of the first 10 calculators, and we have $855.07. The next section that we have is 6.2, and this is called numerical integration. And it says it is important in many applications to find the area under a curve. In this section, we will discuss methods used to approximate the area under the curve of the function and above the x-axis in between two given values. So for us, we are going to have two values here. We'll say from A to another value on our curve, and we'll say B. And from here, we're going to split this and do exactly what we did in the last chapter, is to make some rectangles. And this is what the method that we learned back in chapter 5. And we talked about using either left endpoints, right endpoints, or using midpoints in our intervals. So it says we can approximate the area in a curve by making equal size rectangles, which is again what we did in chapter 5, and adding up each of the rectangles' area. The smaller the width of the rectangle, as n gets larger, the more closely the approximation will be to the actual area under the curve, as shown in the figures below, which again we saw back in chapter 5. When drawing rectangles under the curve, we can either draw the rectangles from the left endpoint, the right endpoint, or the midpoint of the rectangles. And it is usually the case that the midpoint rule gives us more accurate answers. than either the left endpoint or the right endpoint rule. And you can again see that like we did in the last chapter or in those pictures that are here. So we actually have better rules used, and we're going to focus on the next one, which is called Simpson's rule. And this is a numerical method that approximates the value of a definite integral by using a quadratic function. This is based on the fact that given 3 points, so we need to be given 3 points, we can find a quadratic equation, a parabola, that goes through these points. This gives a more accurate approximation to the area under a curve. So this is again called Simpson's rule. So on the next page, we're going to take a closer look at Simpson's rule. So if you see, I have a curve drawn there. And in order to approximate this area, we're going to use what's called Simpson's rule. And Simpson's rule is going to use parabolas. And again, in order to use parabolas, we need 3 points. And so we're just going to kind of put some values in on here, and we'll go ahead and say that this is going to be my first x value. And I'll say here's another x value, x1, another one, x2, x3, x4, and then we'll just put dot, dot, dot all the way until we hit the end of it, which is we'll call x of n. And so this is going to be our first value we call a, our last value we call b, so it matches up to what we did in the rectangular part back in chapter 5. So if I have 3 points, so here's point 1, point 2 when I substitute in x1, and then when I substitute in x2, I can connect these and draw a parabola. And if you notice, it looks very similar to the shape of the curve for the graph. And again, you can do that again when you use x1, x2, and then x3 in the next 3 points, and connect those and draw a parabola. And this gives, again, a better approximation to the area under the curve. So in order to calculate Simpson's rule, we have to take delta x and divide by 3. And we're going to multiply by f of x sub naught, or a value, that starting value, plus 4 times f of x1 plus 2 times f of x sub 2 plus, and then it's going to alternate with the 4's and the 2's until we arrive at the last value that we have. And so plus, and we'll say 4 f of x sub 3 plus 2 f of x sub 4 plus, and this goes on, and we'll say plus until we arrive at 4 f of x of n minus 1 plus f of x of n. And we'll go ahead and close our bracket, and let's add that where delta x is, just from chapter 5 in addition, is going to be b minus a divided by n. And just a note down here, n must be an even number to make this work. We do not get into a proof for this. This is more or less given to you guys, and we're just going to have the formula that is starred up here, and something that you definitely want to write down on your outline that we can be using. The next example says, the manager of a chain of pet supply stores is planning on selling a 10-year franchise. Past records in similar locations suggest that T years from now, the franchise will be generating income continuously at a rate of f of t $1,000 per year, where f of t is indicated in the following table for a typical decade. So you can see we have t, which is our years, and the rate of income flow. So it says, if the prevailing rate of interest remains at 5% per year compounded continuously over the 10-year term, what would be a fair price for them to charge for the franchise based on the given information? So what we need is to find our present value. And back from section 5.5, we have that our present value is going to be the integral, and we'll put those limits of integration on in just a sec, of f of t times e to the, and our rate, and it had to be a negative value, times t. So for us, it's negative 0.05 t. And then again, integrating this with respect to t. Let me put a note that this is going to be from section 5.5. And the limits of integration would be that time period that we have here, which is that 10-year time period, so going from 0 to 10. f of t that we've dealt with before was always a function, and we would just go ahead and substitute in that function and integrate it. But we don't have a function for this problem. Instead, we have a table that gives us the rate of income flow, which is different depending on which year it's at. So from here, we are going to approximate this by using Simpson's rule. So to do that, I need to have my delta x value, which again is b minus a, and on my limits of integration, I'm going to have 10 minus 0 divided by n, which is the number of years that we have, which is 10. And then I'm going to go ahead and say it works out to being 1. So our formula is going to be delta x divided by 3, which is the formula that we have from Simpson's rule, times, and then our first value that we have is going to be 0. So we have f of 0 plus 4 times f of 1 plus 2 times f of 2. So we are going to evaluate this, and in order to do that, I do not have a function to integrate. I am going to have to use my table, and I'm going to go ahead and use the Simpson's rule approximation in order to approximate the area under this curve. I'm also going to go ahead and say that we have our p of v at times t is equal to this integral. So from Simpson's rule, we know that this is approximately equal to delta x divided by 3 times our function, and our function here is PV, our present value. The first time that we have is at 0, plus Simpson's rule then says 4 times our present value of the next year, which is 1, plus 2 times the present value of the next year, which is 2, plus, and this goes on until we arrive at not the last time, but the time before that, plus 4 times the present value of 9 plus the present value of 10. So from here, we have delta x, which is already worked out to be 1. So 1 divided by 3 times the present value at time 0 is going to be f of t, which is 510, times e to negative 0.05 times 0, plus 4 times the present value of 1, which is going to be f of 1, which is 580, times e to the negative 0.05 times 1, plus 2 times f of 2, which is 610, times e to the negative 0.05 times 2, plus 4 times 625 e to the negative 0.05 times 3, plus 2 times 654 e to the negative 0.05 times 4, plus 4 times 670 e to the negative 0.05 times 5, plus 2 times 642 times e to the negative 0.05 times 6, plus 4 times 610 e to the negative 0.05 times 7, plus 2 times 590 times e to the negative 0.05 times 8, plus 4 times 573 e to the negative 0.05 times 9, plus the last term that we would have would be 550, which is our f of 10, times e to the negative 0.05 times 10. So this is very tedious and definitely takes some time. From here, I would substitute this all into my calculator, and when you do, you arrive at 4,796, and the amount that we are measuring this in is going to be in thousands of dollars. So thousands of dollars. So you can say that the income stream over the 10 years is about, and I'll just go ahead and rewrite this as $4,796,000. Which is equivalent to $4.796 million. So the next section that we have is 6.3, which is called improper integration. And improper integration is sometimes it is useful to be able to integrate a function over an infinite period of time. So consider an infinite region S that lies below the curve y equals 1 over x squared, above the x-axis, and to the right of the line x equals 1. You might think that since S is indefinite in extend, the area must be infinite. However, this is not true. In fact, the area of the part of S that lies to the left of the line x equals 1 is, and you can see that as you continue on, that area gets smaller and smaller and smaller. And if you remember from Algebra 2, learning about arithmetic and geometric sequences in series, this should ring a bell. And so we notice that is a at t is less than 1, no matter how large t is shown. And it says, moreover, since the limit as t approaches infinity of a at t is equal to the limit as t approaches infinity of 1 minus 1 over t, we arrive at the area is actually equal to 1. The steps up above are shown too. So we can say that the area of the infinite region S is equal to 1, and we can rewrite this as the integral from 1 to infinity of 1 over x squared dx is equal to, if you notice, we rewrite this in terms of a limit. And instead of having an infinite sign on our limits of integration, we have now replaced that with a variable. And that variable, we are taking the limit of it as it approaches infinity, or negative infinity if it was a lower limit of integration of our function. So we have a couple keywords here. The keywords that we have for this section are going to be convergent and divergent, or converges and diverges. And so to be convergent, an integral is said to be convergent if the integral has a value that is a real number. And then divergent is going to be if an integral is not convergent, then it diverges. A divergent integral does not have a value of a real number, usually because the area under the curve is indefinitely large. So another little note here to remember that we saw back at the very beginning of our semester is that the limit as x approaches either positive or negative infinity of 1 over x is equal to 0. Remember, as something gets really, really large in the denominator, that gets actually very small as a number in whole. So we have improper integrals of type 1, and this is our infinite integrals. It says that if we have the integral from a to t of f of x dx exists for every number t is greater than or equal to a, then the integral from a to infinity of f of x is equal to, and we are going to rewrite this as the limit as t approaches infinity of a to t. And again, that's because our upper limit of integration here is now the limit that we're approaching of our function f of x dx. And this is provided that the limit exists as a finite number. Part B says the integral from a to t of f of x dx exists for every number t less than b. Then we can say that an integral from negative infinity to b of f of x dx is equal to the limit as t is approaching negative infinity this time. Since that is not a number, that is an expression for something very, very large, of t to b of our function integrated with respect to x, provided that the limit exists as a finite number. The third case that we have, which is on the top of the next page, says that if both a to infinity, that integral of f of x dx, and the integral from negative infinity to b of f of x dx are convergent, then for any real number a, we can define the integral from negative infinity to positive infinity f of x dx. So if you notice this time, not just having one undefined limit of integration as infinity or negative infinity, this time we actually have both. So we have a negative infinity and a positive infinity. So we're going to select any value that we want. I'm going to go ahead and select a, and I'm going to say that this is the same thing as saying the integral from negative infinity to a of f of x dx plus the integral from a to infinity of f of x dx, and adding those two together. Since we are talking area, all I did was take that whole entire area and split it into two pieces and add those pieces together to find the total area. So from here, we would then have to use part A and part B on the previous page to evaluate. So then use part A and B to evaluate. So the next definition that we have is going to be the integral from 1 to infinity of 1 over x to the p dx is convergent if p is greater than 1 and divergent if p is less than 1. This is definitely something that you can use to help you kind of solve these problems faster. So we will talk about this. A lot of times students forget that they have this tool in their pocket to use. So we'll talk about what happens if you forget about it, and then a way to kind of shortcut your answers. So the first example that we have says determine if the improper integral converges or diverges. And then it says if it converges, then find the value it converges to. So if you figure out that it diverges, you are done. If it converges, then you have to figure out what it converges to. So if you notice, I cannot evaluate my integral as it is. I need to rewrite this as a limit. So I'm going to say the limit as, and I'm going to call that upper limit of integration b approaches infinity. And we'll say from 8 to b. And again, you can call that anything you want. You can call it t. The limit is t approaches infinity, a approaches infinity. I'm just going to go ahead and use b. And I'm also going to rewrite my integrand as x to the negative 4/3 dx. So from here, I would integrate this. And when I integrate this, my limit is still written. I have not evaluated my limit yet, so I still need to keep writing it. When I evaluate my integral, I'm going to add 1 to my exponent and divide by that same exact number. So when we do this, we have the limit as b approaches infinity of x to the negative 1/3 divided by negative 1/3. And then again, rewriting this so it looks a little bit better. This is going to become negative 3x to the negative 1/3. This is also a definite integral. So I'm going to go ahead and say we're going to evaluate this from x equals 8 to b. So from x equals 8 to b, and from x equals 8 to b. So from here, I still have my limit. So it's still the limit as b approaches infinity. And I'm going to now evaluate it at my upper limit of integration. My upper limit of integration is b. So I have negative 3b to the negative 1/3 minus, and then evaluating this at the lower limit of integration, which is just 8, is going to be negative 3, and then 8 to the negative 1/3. So from here, before I actually evaluate my limit, I'm going to rewrite this. My exponents are negative, so I'm going to go ahead and move those bases to the bottom, to the denominator, and I'm going to have limit as b approaches infinity of, and this is negative 3 over b to the 1/3. This is going to now become plus 3 over 8 to the 1/3. From here, we can take the limit of each term, but if you notice this second term is just a constant, it's just a number. So we have the limit as b approaches infinity of negative 3 over b to the 1/3 plus, and then this is just a constant. And remember, the limit of just a constant is just a constant, and this is going to be the cube root of 8, and the cube root of 8 is just 2. And when we look at this limit here, the limit as b approaches infinity, you would have 2 or a negative over something very, very large. And having a very large number in the denominator means that this would approximately equal 0 plus 3 over 2. So our answer would work out to be 3 over 2. So this converges. And remember, by definition, converges means that it converges to a number. And now I wanted to bring your attention to the definition that is written right up above. And with this definition, it is another way to think of these problems. And I told you that this is a little bit of a shortcut way to think about the answers. And I want you to notice that it says 1 over x to the p dx. And this is the integral from a number to infinity. And if you notice, we have a number to infinity. And if you look at this, the value of p in this problem is that exponent, which is 4 over 3. And 4 over 3 is definitely greater than 1, which means that it should converge by this definition. And that is what we had. It does not tell us the value that it converges to, but it does tell me if it converges or diverges, and allows me to kind of go forward with the problem knowing that. So since it converges, I know that I should have a numerical answer, and diverges means that it would either be infinity or negative infinity. So the next example that we have says determine if the improper integral converges or diverges, and if it converges, then find the value it converges to. So this would be rewritten as the limit as, and I'm going to call it a approaches negative infinity, and then it's going to be the integral from a to negative 4, and I'm going to rewrite my integrand as 3 x to the negative 4 dx. And I am able to integrate this just by using the power rule. So again, we haven't yet evaluated our limit, so that still stays there. And when I go ahead and integrate this, I'm going to add 1 to my exponent, and I get negative 3. And again, divide by that same value. And then evaluate this from x equals a to negative 4. And then from here, I'm going to clean up what I have written. So I still have my limit. And my 3's are going to cancel out, and I just have negative x to the negative 3rd. And so I'm going to rewrite this as negative 1 over x to the positive 3. And again, evaluating this from x equals a to negative 4. From here, I'm going to go ahead and substitute in my upper limit of integration, but again, do not forget to write that limit. When I substitute in my upper limit of integration of negative 1 over negative 4 raised to the 3rd power, make sure you put that negative 4 in parentheses, minus, and then I'm going to go ahead and substitute in a, which is my lower limit of integration, so over a to the 3rd. From here, I'm going to simplify this a little bit, and again, remember that that limit does not change that constant value that we have. So for the first one, I have negative 1 over negative 64. Then it's going to be plus 1 over a to the 3rd. And so with this, from here, I get the first term is just a constant, and so that would just stay positive 1 over positive 64 when those negatives cancel. And then taking the limit of that second term, that is going to go off to 0, just like what we did before back in the very beginning of the semester. And so from here, we end up with 1 over 64. And so this also converges. The next example that we have says determine if the improper integral converges or diverges. And if it converges, then find the value it converges to. So I'm going to go ahead and rewrite this, and then we can take a look at the definition also that was on the previous page, because this is written in that form. And so from here, I'm going to rewrite this as the limit as, we'll say b approaches positive infinity. This is going to be the integral from 27 to b of, and I'm going to rewrite this as 2 x to the 1/3 power, and again, since it's in the denominator, it would be negative, and then dx. From here, I'm going to leave my limit, not evaluating the limit yet, and then actually integrate using the power rule. So I have a 2 out in front. I'm going to add 1 to my exponent. When I do that, I add 1 to negative 1/3, and I get 2/3. And then I'm going to divide by that same value, which is the same as multiplying by the reciprocal, which would be 3/2. So the reciprocal of 2/3 is 3/2. Again, feel free to write it the other way and then have that extra step in there. We are going to be evaluating this from x equals 27 to b. My 2's are going to cancel here. I am going to evaluate my limit in just a minute, but I first need to evaluate this from my upper limit of integration to my lower limit of integration. And so that upper limit of integration is 3. It's going to be b to the 2/3 minus 3 times 27 to the 2/3. And again, this second term that we have is just our constant. But when I substitute this in, you will notice that I'm going to have the limit of b as it approaches infinity of 3b to the 2/3 minus, and then we have 3 times 27 to the 2/3, which again, this is just a constant. So this part that we have right here, if you were to substitute in something very large, as this b gets very, very large, approaches infinity, if you have infinity to some power, it's still going to be extremely large. It would still be an infinity times 3 would still be an infinity. So this is really, really big. And then minus a number, it doesn't matter what this number is here. I'm just going to say minus a number. This is still going to be something extremely large. So this means that this is going to diverge. And again, using that definition that we had up above, if you were to look at this and notice that this is going to be x to the 1/3 in the denominator, and this is my p-value, and since p is less than 1, since p is 1/3, that means that this should be diverges. So from here, if you notice that that definition works, you could have skipped all of this work here and just written the word diverges and stated that it's because of the definition. Okay, so you can always state because of the definition. So the next example that we have, I'm going to go ahead and circle, and we'll work on that one together in class. And then we have another example right below. And if you notice this one, it says determine if the improper integral converges or diverges. And if it converges, find the value that it converges to. So looking at this problem, I have the integral from 0 to infinity of 1/4x plus 1 to the 2nd power, and then dx. So I'm going to rewrite this. I have a little bit of an issue though with this problem. So from 0 to infinity, I'm going to rewrite as 4x plus 1 to the -2nd dx. And I cannot integrate this how it is, so I'm going to have to let u equal that inside function that we have. Notice that I have an inside function and an outside function, and du is equal to, taking the derivative of this, 4 times dx, solving for dx. We have dx is equal to du all over 4. And then also remember that when we do this, we have to change our limits of integration. So before I do this, I'm going to go ahead and rewrite this as the limit as b approaches infinity. And I'm going to have from 0 to b of 4x plus 1 to the -2nd dx. And substituting in my lower limit and my upper limit of integration, I'm going to change those since I did change my variable. And when I do change this, my upper limit of integration, I'm going to substitute in b. So I have 4 times b plus 1, which would stay just how it is. And then my lower limit of integration would be 4 times 0 plus 1, which works out to be 1. So my new limits of integration on this are going to be the limit as b approaches infinity of, and this time I am integrating from, it went from 1 to 4b plus 1. And then the new problem that I have here, my new integrand is going to be u to the negative second times dx, which is the same thing as du over 4. So from here, I need to actually integrate this with respect to u. And so I'm going to write my limit as b approaches infinity. I have a 1/4 times adding 1 to my exponent. I have negative 2 plus 1, which is negative 1, and dividing by that same value. And then I'm going to evaluate this from u equals 1 to 4b plus 1. So again, simplifying this, we have the limit as b approaches infinity. And it's going to be negative 1/4, and that u would also go into the denominator from u equals 1 to 4b plus 1. So I cleaned up my integrand, which I had, and that expression, and now I'm going to evaluate it. Again, still writing limit, since I have not yet evaluated this limit yet. So I have negative 1 over 4 times 4b plus 1 minus, and then negative 1 over 4 times 1. And again, the second term that we have in this problem is just a constant. And so if you were to take the limit of that first term, you will notice that b is approaching infinity. And since it is in the denominator, we know that this is going to approach 0. And so we have 0, a negative and negative would become a plus, 1/4. So we arrive at an answer of 1/4. And this converges. So this one also converges to a value. On the next page, we have another example. And for this one, if you notice, we have going from negative infinity to positive infinity. So we are going to have to split this at a value. And I usually pick a value of 0 to split this and rewrite it. So we will look at this one together in class, but think about how you could rewrite this before we move into the rest of the problem. Right below the example, it says, in certain economic situations, money flows into and out of an account almost continuously over a period of time. Let the continuous function f of t represent the rate of flow of money per unit of time. If t is in years and f of t is in dollars per year, the area under f of t between 2 points in time gives the total dollar flow over the given time interval. So the first definition that we have is the total money flow. And it says if f of t is the rate of money flow, then the total money flow over the time interval from t equals 0 to t equals capital T is going to be given as the integral from 0 to capital T of our function f of t with respect to t. Right underneath this, it says the total money flow does not take into account the interest the money could have earned after it is received. It is simply the total income. So an amount of money that can be deposited today at a specific interest rate to yield a given sum in the future is called the present value of a future sum. So definitely one of those words that we need to know. It's present value. The future sum may be called the future value or the final amount. So the next definition that we have right below that formula says if f of t is the rate of continuous money flow at an interest rate of r for capital T years, then the present value is, and we're going to go and write PV for present value. It's going to be the integral from 0 to capital T of our function with the money flow, f of t, but again taking into account that interest rate, and since it is compounded continuously, it's going to be e to the negative rt dt. And it says right below this, an accumulated amount of money called A represents the accumulated value or final amount of the money flow, including interest received on the money after it comes in. Recall that total money flow does not take into account the interest. So right below this, it has the accumulated amount of money flow at time capital T. And it says, if F of T is the rate of money flow at an interest rate of R at the time T, then the accumulated amount of money flow at time capital T is going to be, call this A, is equal to, and we take into account, it's going to be E R times capital T. And then we're going to integrate our function, which is that present value, which is going to be from 0 to capital T, our time of F of T, e to the negative R T dt. The example on the next page says the following function represents the rate of flow of money in dollars per year is F of T equals 800 e to the 0.05 t. Assume a 10-year period at 8% compounded continuously and find the following. Part A is asking for the present value, and then Part B is asking for the accumulated amount of money flow at t equals 10. So I'm going to go ahead and do Part A first, and this is asking for the present value. And if you go back on the previous page, you will see the formula for present value, and I'm going to copy that down. It is the present value is equal to, and it is the integral from 0 to t of F of T times e to the negative R T dt. And so for the function that we have for this problem, we know that F of T is equal to 800 e to the 0.05 t, and we also know that we have a 10-year period, which is stated up here, 10-year period, and it's compounded at 8% continuously. So putting all these numbers into my present value formula here, we are going to have the integral from 0 to 10 of F of T, which is 800 e to the 0.05 t times e to the negative RT, and again R is 8%, and rewriting that as a decimal, we'd have 0.08 t dt, and that value is also negative there. So from here, we are going to rewrite this. You can move the 800 out in front, and we have the integral from 0 to 10. You can combine our e to the exponent that we have because they have the same base. And so doing that, you're going to add together your exponents. And so we have 0.05t plus negative 0.08t, which works out to be an e to the negative 0.03t dt. And we can integrate this from our formulas that we had back in last chapter. And this is going to be e to the negative 0.03 t divided by that same value, negative 0.03. And again, we are going to be evaluating this from t equals 0 to 10. And then from here, we would have 800 divided by negative 0.03. And then I would substitute in 10. So negative e to the negative 0.03 times 10 minus e to the negative 0.03 times 0, which is just e to the 0, which would just be 1. And then working this out on your calculator, and then since we're dealing with money, we would round 2 decimal places. This is going to be the dollar amount of $6,911.51. Part B is asking for your accumulated amount of money flow at time t equals 10 years. So the accumulated money flow is equal to A equals, and it's e to the RT times the integral from 0 to t, and then F of T, e to the negative RT dt. And again, that is listed up above. And from here, I'm going to go ahead and substitute in the values that we do know. I have e to the R. R is still 0.08. T is our time. It's a 10-year time period. And then we're integrating this from 0 to 10. My function again is 800 e to the 0.05t times e to the negative rt, which is negative 0.08t dt. From here we can clean this up. This value out in front, if you do 0.08 times 10, will be e to the 0.8. You can also move that 800 out in front too. And then again, this is going to be the integral from 0 to 10 of, and then combining these together, we get e to the negative 0.03t dt. Integrating, we arrive at, and I'm going to rewrite this as 800 e to the 0.8 times, and this is going to be e to the negative 0.03t divided by that same value. And then evaluating this from t equals 0 to 10. And then we end up with 800 e to the 0.08 divided by negative 0.03, since those are all just a constant value. And then we're going to substitute our upper limit of integration, which is 10, minus substituting in 0, we have e to a 0 power, which would just be 1. And then working this out, we arrive at $15,381.85. Right below this is the capital value. She'll give that a star. And the capital value of an asset is the present value of all future net earnings of that asset. If R of t gives the annual rate at which the earnings are produced by an asset at times t, then the capital value is given as the integral from 0 to infinity of R of t e to the negative rt dt, where r is the annual rate of interest compounded continuously. So the next example that we have says an investment produces a never-ending stream of income with a flow rate of R of t equals 1000 e to the 0.02 t. Find the capital value at an interest rate of 7% compounded continuously. And again, it wants that capital value here. So I'm going to go ahead and zoom in, and I'm going to rewrite that formula that is right up above. And so our capital value is going to be the integral from 0 to infinity of R of t e to negative rt dt. And then substituting in what we do know, we know that we have the integral from 0 to infinity. R of t was given to us right up above. It's 1000 e to the 0.02t times e to the negative 0.07. So writing that percent as a decimal, t dt. And then from here, again, just like what we did in the previous example, cleaning this up a little bit, we would have the integral from 0 to infinity of 1000 e to the negative 0.05t dt. And we cannot evaluate this. This is an improper integral, so we need to rewrite this in terms of a limit. I'm going to say the limit as b approaches infinity of 0 to b of 1000 e to the negative 0.05t dt. And then integrating this, again, we have not yet evaluated our limit, so we want to make sure we rewrite that limit. And then we would have of 1000 times, and it's going to be e to the negative 0.05t divided by negative 0.05. And we are going to evaluate this from t equals 0 to b. So substituting in my upper limit of integration, again, rewriting that limit, we are going to have 1000 divided by negative 0.05, which works out to be negative 20,000. And then we have e to the negative 0.05b minus, and then negative 20,000 e to the 0, which would just be 1. So I'll leave it like that. And so from here, we have the limit of the first term that we have, and the limit of this value as e goes off to infinity or as negative infinity. This actually approaches 0. And you can go ahead and take a look at an exponential graph to kind of get a better sense of that if you don't remember that back from the limit section. And so from here we have this is equal to 0. Negative and negative would make a plus, and then we have 20,000. And so working this out, we get $20,000. So this is the capital value that we would have.